Greetings everyone, and welcome to the third BOVA Open Network meeting, brought to you with the support of the Global Health Network. I'm Fiona Shenton. I'm the BOVA Network facilitator, and I'm going to be joined as co-host by our co-director, Steve Lindsay. Well, as you can see from this slide, we've got a packed agenda where Steve will give an update on BOVA's achievements, and then we'll hear reports from each of our 8 pump priming projects. And finally, Lucy Tasting will outline briefly where we see BOVA's future before we close the meeting. The pump prime projects are divided into 3 broad themes of basic science, new tools, and community engagement. And at the end of the presentations from a theme, there'll be a panel discussion where we'll put your questions to the speakers. So I think we should dive straight in and get going with Steve's presentation of BOVA's achievements.
Well, good morning, everyone. Good afternoon, everyone, and possibly good evening, everyone. I thought I'd start off by being very broad and explain to newbies what BOVA is about. It's a network which is focused on building out vector-borne diseases in sub-Saharan Africa. That's how we derive our acronym. And the basic issue for those who don't know anything about mosquito-transmitted diseases or bug-transmitted diseases, that these are a collection of really important diseases. They threaten over 80% of the world's population with at least one of these infections, and half of the world's populations are threatened by at least 2 or more. And there are particular problems in poor communities, and in sub-Saharan Africa, they are a major impediment to health. And what we're interested in within the network is to look strategically at how we could make homes and communities safer against these ragbag of diseases. Now, in sub-Saharan Africa, the focus of the network is on 2 broad areas. One is malaria, which tends to be a more rural disease and peri-urban around the outsides of settlements. And then in urban areas, sort of dengue and a bunch of other diseases as well. So what I mean by a bunch of other diseases is dengue, hemorrhagic fever, Zika, yellow fever, chikungunya, shown here. The commonality is not the diseases, but what's transmitting them. And that's the mosquito in the heart of this, which is Aedes aegypti, which is probably in every town and city throughout the tropics and undoubtedly widely spread in sub-Saharan Africa. So the issue is about defending ourselves against malaria mosquitoes in rural areas and this mosquito in urban areas. And what we're trying to do here is fuse a new discipline between a bunch of experts from that understand things about the vectors, the mosquitoes, and those that understand the built environment. And it's a fertilization of ideas. And I hope that in this session today that you'll see just how effective that can be. So what have we achieved? Well, we have nearly 500 members. We were in the great position, which is unusual for any academic, of giving out money to projects. So this was and we're here from these 8 pump priming projects later. We've also interested in funding for the future to make sure that this network continues. So we funded grant writing workshops for people to get funding for the future. And at the same time, we're advocating what we're doing at the highest levels internationally and producing scientific publications as well to show the evidence for what we're doing. And particularly, we're concentrating on simple messaging. What can we do now to make our homes, cities and towns more resilient against the threat of these diseases? So let's have a look at the membership. And congratulations, East Africa, because you have the highest membership of people. So we think that's great, but you can see that there's a worldwide distribution of members. So with the pump priming projects, we selected grants according to 3 different areas. basic science to understand the fundamentals about this. And a lot of what we're doing is understanding how human odors move in the built environment, because it's that line, those chemicals that insects follow in order to bite and infect people. So understanding the movement of volatiles in a building will provide an insight into that. We need new tools. So there's all sorts of innovative new tools that are being looked at. And finally, getting the communities involved and scaling up also needs to be considered hugely important. So where and what have we funded? Well, in these apricot bunch of basic research, there was fluid dynamic modeling that's been done in the Gambia and I think in Malawi as well. There's a study which looking at the effect of height on mosquito entry and actually filming individual mosquitoes and how they orientate into houses in Malawi. The second bunch is the new tools. So we'll hear about new floors for control of fleas in Kenya. We'll hear about spatial repellent chairs in Tanzania and novel ways to use insecticide treated netting in Mozambique. Then finally, involving work with the communities, it's about actually working with social housing in Ethiopia and a really innovative idea of how to reduce mosquito habitats in urban areas by turning trash to treasure. So that's number one, the pump priming projects. We've also been supporting grant writing workshops in basic science, in multisectoral and scaling work up as well, and in new tools. And we hope that some of those initiatives will develop future finance and in the future and actually be going live and continue this working relationship between those from the two sectors, those in the vector science and those in the built environment as well. We've also done a lot of work with international partners. We had a conference at UN Habitat and we're working closely with them. We have RBM, which is an umbrella organization of 500 interested parties that will work on malaria control. We're working with WHO, the Global Vector Hub, and importantly, PAMCA, which is Pan-African Mosquito Control Association. So what are we doing? Well, with WHO, we're engaging with WHO to advise on updates to the healthy housing guidelines, because until now, nobody's considered the problems of mosquito transmitted diseases in around the house. And that is absolutely ridiculous that that's not considered, because that's where transmission occurs, either in or outside buildings, particularly the homes. Working with UN Habitat, we're working on a training manual for the international guidelines, so they're actually giving guidelines to how to build for the future. So this is planning for the future, and we have incorporated some of our ideas into that. We're working with Commonwealth mayors through the Commonwealth Local Government Forum, and working with PAMCA as well. And we're particularly interested in to continue the progression of BOVA under the umbrella of working in association with PAMCA. And then finally, rollback malaria, where we've got 2 working groups on vector control and intersectoral work, where we have a large presence thinking about the built environment. So what are we doing? Well, for the future as well, we're extending our contributions of members. Some of us are writing a Lancet Commission on mosquito viruses in cities. So the Lancet Commission is a very prestigious document, and this will focus on Aedes transmitted diseases in towns and cities. And again, it's a very multi-sectoral approach, bringing in those working in the built environment with those experts on health. We've got working groups in RBM, working with WHO in strategic technical advisory groups on neglected tropical diseases. So neglected tropical diseases includes diseases like dengue. we're collaborating on international guidelines on urban and territorial planning. So these are not just in health, but they're in the built environment that we're influencing as well. And at various international meetings as well around the world at high-level conferences. So the publications have been grand over the last 2 years. Some of them are shown here. And one of the ones which I think most members contributed to was one which is in press at the moment with Philosophical Transaction for the Royal Society B, what a great name, where we're looking at a mnemonic called DELIVER. And this is captured here in this very short graphic here. So what we're advocating is screened doors, which are self-closing, eaves, which are either closed or screened, lifting the house, L is for lifting, I is for insecticidal nets or IRS, because it's a major component of mosquito control in rural environments, and we don't want to let that down. The importance of ventilation, of cross-ventilation, having at least 2 large windows in a house, to clean up the domestic environment, to prevent breeding of Aedes mosquitoes in domestic environments, and to keep a clear and tidy roof where we don't get aquatic habitats being produced where mosquitoes can grow. So that's the sort of thing that we're doing. Here's a list of publications. I'm not going to go through them in detail, but just highlight that we're published publishing in very high-rated journals: Lancet Planetary Health, Nature Scientific Reports, Nature itself, PLOS Medicine, and PLOS Neglected Tropical Diseases. So these will be and are influential documents going out to the scientific audience. For those of you that would like to know more about our network, please look at our website. And for those that are tweeters, look at, you can tweet us on @BOVA Network. So finally, I think to acknowledge the funders, this is a GCRF grant, Global Challenges Research Fund, which is a coalition of grant funding organizations in the UK on basic science, human health, and on the natural environment as well. And we're very grateful for their support. And that's all I want to say at the moment. So back to you, Fiona.
Thank you very much, Steve. So we will go on to our first theme of the day, which is the basic science. So we will be hearing talks from Jakob Knudsen about computer fluid dynamics modelling of indoor climate, from Jeroen Spitzen, who is filming mosquitoes in Malawi, and Majo Carrasco-Tenezaca, whose project in the Gambia was looking at whether or not raising houses would affect mosquito entry. So we'll start with Jakob. Thank you.
I'll do this presentation together with Daniel Sang-Hoon Lee, who's an associate professor also at the Royal Danish Academy. We have been looking into CFD modeling of indoor climate in rural sub-Saharan African houses. We'll share the presentation. I'll make a few points here in the start. First of all, that we are interested in climate, we are interested in buildings, but we know that buildings are very different. The needs of a building are very different from one climate zone to another. And in order to understand this, you can use a number of tools. One of them is the human thermal comfort zone. It's a tool where you try to understand the relation between air movement, temperature, and humidity. And it's basically saying that if it's very hot, the only thing you can do is to add an insulation to make you feel good. Air movement is why you go to the beach on a summer day. It cools down your body and you feel more comfortable. So that's what you can do also inside a house. One of the tools we have to do this is computer fluid dynamics. This is one of our early pictures. We did this maybe 2 years ago, trying to understand the relation between carbon dioxide coming from a human's breath and how it's related to the building. You can see how it's coming out through the doors and eaves in this house. But this was a rude model. It's a crude model, and then Daniel will talk a bit about how we have tried to improve this model. Daniel.
Yeah, thank you, Jakob. I'll just, yeah, hope you can see me now. So this is actually our first experiment house built in Tanzania. We construct this house to for the purpose of CFD model setup configuration verification. So we built this house. You can see that this is a solid wall with open windows and doors you can open and close, and it's actually cross-ventilated, which means that windows on the other side as well. Simple steel roof, corrugated roof, and then next slide, Jakob, possibly. And within this house, this is how we set up our devices. We try to set up as many devices as possible to obtain the most data. But for this presentation, the most relevant probies are the CO2 HOBO devices, which is the green ones. And you can actually, well, actually, sorry, you can't see my mouse because Jakob is controlling, but it's the box in the center is actually the bed, and then around it you can see 4 CO2 1, 2, 3, 4 in the clockwise. That's where we place the CO2 devices, and then CO2 device number 5 in the center is actually about 1.8 meters high from the ground, and is within the bed net. So we just wanted to also check how the CO2 is within the bed net, also outside the bed net. And this is a photo showing how the devices were set up within the test house. We have airflow sensors in both windows to see, to measure the characteristic wind movement in and out of the building as well. And on the right-hand side corner, you can actually see the devices in different heights. So 3 devices near the bed is actually closer to the ground to see how much CO2 has been dropped to the ground level. And we also have 2 CO2 devices at in the mid height of the window, which is about 1.6 meters from the ground. And I told you the other one is within the bed net at 1.8 meters from the ground. Yep. And this is the data we measured. So this is, we measured over about five days. This is just on the left, is just showing the typical plot of one day, which is on the 24th of September. You can actually see that the CO2 measurements at 1, 2, and 4, which rises gradually after the sleepers came into the house around 8 o'clock. You can see that number 5, which is within the bed net, showing a lot of fluctuations during the sleeping hour. Before you can clearly see the patterns and the movement of the fluctuation of the CO2 measurements within the sleeping hour, which is bounded by the 2 dotted black lines. On the right-hand side is actually the measured air velocity in and out of the house. We can actually see that during the sleeping hours, which is marked with dark gray, when we started those measurements, the 2 doors are closed so that you can actually see that there's relatively subtle, very small fluctuations. But during the daytime, where all the windows and the doors are open, you can see that there's high wind movement variations, also gust of wind moving up to about 6 meters per second. Next slide. For computation modeling, this whole experiment setup was important to verify the CFD configuration with against the field data, because we actually have the bed net. So we want to also check how the CO2 movement in and out of the bed net. The bed net we used has about 60% air attenuation property, so we should be able to translate that property into computation model. Jakob did the experiment test before with that bed net in a wind tunnel, and we made a digital twin, we call it, in the safety simulation, and then we actually tweak the so-called porous germ boundary parameters to mimic that result, where you can actually see in this diagram that the wind is coming in from the left-hand side towards the right-hand side. In the middle, there's a porous germ boundary condition, which is a mathematical model of the bed net, and then we change the parameters until we get the 60% attenuation on the right-hand side. Next slide. This is now, we're going a little bit more in detail of our CFD simulation setup. On the left-hand side, you already saw our actual physical house construct in Tanzania that is translated into a digital model. All the dimensions and everything has been checked, so they are quite detailed and accurate, though we have to eliminate that overhang of the roof because we are more concentrating on the indoor climate this time, and then the indoor and outdoor exchange of the air, which is only happening in the window. On the right-hand side, you can see that there's a mannequin, very simplified, geometrically simplified mannequin within that bed net. Of course, in real life, the bed net has more wrinkles, and also it's a tension structure, so that it sags under its own dead weight, so there's a lot more curvature. But at the moment, we have simplified because the impact of that small details on the surrounding air velocity and the CF carbon dioxide movement is a little bit minimal. Next slide, please. This is safety boundary conditions. So most of these measurements are based on empirical data, which we put into CFD simulation as input parameters, and then we get the result from these input parameters. The right-hand side, we can actually see that they are the CO2 input of about 435 ppm, which is a daily average, and then XL, which is air coming out of the modeled as air coming out of the mannequin at about 0.77 meters per second. In real life, of course, a person breathes in and out, and there's a sinusoidal effect profile, but you can that peak value can hit up to 1.8 meters per second. But we can actually, there's a previous research done that 0.77 meters per second constant acceleration will give the similar effect. We also put energy boundary condition, the temperature boundary condition with body about 309 Kelvin. The breath temperature is about 306 Kelvin. We had measured the ground temperature, which is also included in the simulations, and also background ppm, CO2 ppm, as we discussed before. The inlet velocity, yeah, there you go. We're going to talk a little bit more about that. This is first result with, on the left-hand side, this is average inlet velocities. On the left-hand side, the window, through the window, the wind comes in and it leaves on the right, but then there's a suction can happen so that also in the outlet, the wind can suck in and come in. You can actually see that this is a steady state simulation where we are assuming that there's a constant flow of air. We checked the CO2 measurement at those 5 probe locations, and we had quite high accuracy on the lower level near the ground, but where the window and more forced convection is happening, the discrepancy was higher. We had a more detailed discussion with other scholars, and then it's mainly because the steady state analysis. On the right-hand side, if you assume that there's a minimum velocity of maybe 0.1, even lower, you can see that there's a large change of wind velocity and the CO2 distribution inside the house. Just to tell you in more detail, the arrows are actually showing the velocity vectors, and then the color contour on the background is showing the CO2 ppm. So we just wanted to plot both on the same diagram so that it becomes more informative. We did for the verification study, then if it's a steady state, how do we actually reduce the discrepancy of our simulation setup in all probe locations? At the moment, the lower ground level has very good agreement, about 90 to 95% agreement with the field data. But then where the influence of the wind is stronger, the discrepancy can be as big as 20%. And we did some simulation. We did a lot of turbulence model check, boundary condition check, meshing check, a lot of parameters. And the main key effect here is that if the steady state is showing some kind of a let's just say airflow state in a more equilibrium, balanced state, by reducing this, the inlet boundary conditions, we can actually pick up good approximation in all area of the house, including the area where most affected by the forced convections. So you can see that on left-hand side, that's a graph showing where in the reduction factor is 1. That means just is a full average inlet velocity applied. And as we apply the reduction factor, as it reaches about 0.2, you can actually see that the CO2 measurements at location 5 and the location 4, we actually drops. We can actually see that all the 4 locations, the measurements comes around 95% accuracy. Location 4 still, it's about 20% accuracy, but that specific location, actually the measurements didn't really change for 5 days. And we are a little bit wondering, during the daytime, during the nighttime, actually there was no change of CO2 measurements. So we are not quite sure whether how accurate that Pro-B readings were. But at the moment, just applying the 20% of the inlet velocities, we can increase the accuracy. So this is actual final plot of a CO2 distribution in a 3D. And those number 1, 2, 3, 4 is hidden at the back, and 5, where all the data has been verified with the field data. So we checked now our safety simulation setup configuration, and using this safety configuration, we're gonna now start. We have started and we have completed. We call it parametric studies of architecture parameters, and based on that, we want to develop a web-based tool where basically we're going to now change the architecture parameters such as building dimensions, location of the windows, length, where the sleepers are. Of course, these are all can be changed, and then run a lot more simulations, and then we collect the data, and then we're going to find equations that can simply plot the CO2 distribution in this 3D space. And then we're going to upload these equations and we're going to make into a web-based tool where a user who doesn't have any idea about safety, it's okay. You can just basically select specific architecture parameters to map. As you can see, the CO2 distribution, as for example, this one, using just that simple equation. So this is the safety data. We're going to slice them into a number. We're going to analyze. Maybe we can go to the next slide, Jakob. We can plot these, and then there's a different CO2 distribution in that plane, section planes, when we're going to make them into equations. And then this equation will, of course, should be updated when we change the geometry of the house. So if you go to the next slide, this is an example where the house has made in 2 meters longer, or we say deeper. Then of course, CO2 distribution changes. So we're going to update this equation with those parameters, length and width and the position of windows, update the equations in the future, and then continue to make more user-friendly web-based tools who doesn't need to know anything about safety. That's our final goal.
Thank you. And I'll come with an example. We have earlier made this Healthy Homes project where we looked at indoor climate changes caused by bed nets. And I'm going to take you to a small tour where I'm showing what a CFD tool can be used for, how to verify other data. We know that one of the reasons why bed nets are not being used so much is probably discomfort in many cases. That was the reason why we started to look at houses some years ago in Tanzania and the Gambia. On one hand, looking at the African houses, which are often quite heavy in the walls with small openings, little ventilation, houses with a high thermal mass and quite uncomfortable sometimes at night, little openings. It makes it difficult to use a bed net. This is from Tanzania, but you find these houses all over Africa. In contrast, we also looked at houses in Thailand and the Philippines, where you find a completely different building style, as this one made from bamboo, which is light and air can move in all directions, and they're quite comfortable. So we tried to understand why houses under similar climate have different properties. And we could see that the temperatures, for instance, inside the house were really different, several degrees under similar tropical conditions, all probably caused by the nature of the building. We started to experiment with buildings, try to modify African houses to see if we could make them perform Asian, so to say, by changing roof or cladding. We started to make digital prototypes on top of the physical prototypes and model indoor climate. And we could kind of come up with this scale of houses where it goes from a standard house, which was quite hot, to houses that would be like the Asian houses, which would perform much better in a tropical climate in terms of keeping the occupants cool. This was translated into a set of buildings in Tanzania, the Magoda project, where we built 6 prototypes, first some in bamboo with raised floors, also 2-story versions of the same buildings. This is from the inside. And we made wooden type where you see the boards are kind of separated by small spaces to allow air coming in. And we made the most radical in a netting material, shade net, which is allowing air to move very easily inside the houses and cools off the building. This is the single-story house in shade net. What we saw when we looked at these houses was that there was a huge reduction in our houses in the number of mosquitoes inside. But we could also see that there was difference between the shade net houses and the timber houses. So it seems like there was the shade net houses were performing better than the timber houses for some reason. They were all performing much better than similar reference houses or modified houses. So now we have tried to simulate the same houses in the new CFD tool. So we have looked at indoor locations, these sections, and we have looked at outdoor outlet locations. And here we have the comparison shade nets versus timber facades. This is the sections inside the house. You can see on the left is the shade net, and on the right it's the timber facades. And you can see that there's a quite different pattern of carbon dioxide inside the house. It's higher in the timber facade houses. And you can also see, if you look at the eaves, that there's more CO2 coming out of the timber facade houses compared to the shade net houses, making it more attractive to mosquitoes. But not least, you can see, if you look at this, this is kind of, it's a bit difficult, but this is the facade. This is the facade of a shade net house, and this is the facade of a timber house. And you can see how the CO2 is distributed. On the shade net house is kind of completely evenly distributed. So there's not much for a mosquito to look for. Whereas if you look at the timber house, you can see that in these small cracks, in some of them, this is a kind of a, this is a zoom in, you can see that the concentration is actually quite high in small points, probably making it more attractive to mosquito that they can find it. So this is what you can see with this kind of tool. You can go very close and see what is happening, not only on a space scale, but also on a local, almost fabric scale. This is the temperature inside the house. You can see that it's hotter in the timber house compared to the shade net if you look at a section like this. And we're using this knowledge to our new generation of houses. We are building 110 houses in the southern part of Tanzania at the moment. And this is where we go next to test this tool to compare, to measure these houses, the indoor climate, and compare it to the digital twin, which is the CFD tool, and see if it performs right. So we are building these 110 houses in rural villages to compare not only malaria, but it's a big randomized control trial where we're looking for a number of diseases and how an improved house can contribute to the decline of diseases. So overall, we have done a reliable CFD model. We are able to predict indoor climate using standard building components. We can also look at interventions like eave tube screenings of windows and stuff. We have partly done that. We have been looking at different building materials. We have been looking at geometric changes. We could still look more at that. And we know now a lot about spatial CO2 concentration and how this might possibly influence mosquito behavior. And we are making this publicly and freely accessible tool soon to come. There's been a lot of people involved in this. Daniel, Thomas, Thiago from KDK, Steve Lindsay, Lawrence from Sideland, and Salum Masabu from CSK Research Solution. Thank you.
Thank you, Jakob and Daniel. Really fascinating insight there with your sophisticated equipment and modelling. That's great. And it nicely leads in now to our next talk from Jeroen Spitzen, who has been filming mosquitoes. So Jeroen, over to you.
Yes, thank you, Fiona. Thank you very much for having me. It wasn't me, myself, but it was a whole team of people that were trying to film the mosquitoes in Malawi, and I'm proud to present some of the results that we have today. I see there are more than 100 people online without emitting more CO2 into the environment that we would have done if we would go to Morocco. Of course, I would love to have to see the BOVA network together, because I think this is an excellent team of people. There are other people online from this team, so you can also ask them questions in the chat. So as you can see, there's a great interest in house improvement as a malaria intervention. And we, with this BOVA study, would like to see how do the different improvements and the designs of the houses affect the mosquito behavior. And as such, we would like to address this using video recording rather than measuring endpoints and finding how much mosquitoes we find in the house. But we really want to see what is the mosquito doing when it's approaching such a house with different modifications of this house. So the eave is a well-known entry point of the mosquitoes, and we filmed this for the first time in a study in Kenya. We are looking from below here at the dark gap, but the eave is also a knowledge gap. So we know, as Jakob and Daniel already presented, that the air currents and the odor plume structures are coming from this eave, but of course also from the windows. And when the eave is open, mosquitoes pass in a split-second hub. There it went, if you see in the movie. But what if we modify the design of a house? If we block the screens or the eaves with screens, or we completely block them with a different home design, would it affect the capture of the mosquitoes that are still flying around outdoors? And also, can we think of other eave control measures, such as eave tubes, when we have more detailed information of these mosquito flights? So that was the objective of our study. So to characterize the mosquito flight paths near a house when they are approaching the house, and we would like to do a 3D reconstruction of these flight paths with the different modifications of the house. And we would like to determine the effect of the closure and the screening, and really find the different flight parameters when the mosquitoes do enter, but also when they do not enter, and for how long will they hang around this house. So to build out mosquitoes, we went, in this case, to Malawi, where there already was a project on house improvement. But first, of course, we had to build the screen, because we were releasing Anopheles gamma mosquitoes, and we don't want to release them in the fields. So we built a screen house, and with Mr. Sanjika making the screening, we had a small home next to it where we put our computers for the cameras, and we have an experimental house here. So inside the screen house, the experimental house, the camera is protected by the roof and infrared lighting here, and we were releasing 500 hungry female mosquitoes each night, and had 3 pairs of sleepers that randomly, in different orders, slept inside the house under a bed net, and we were tracking the mosquitoes from 8 p.m. till 4 o'clock in the morning. Online recordings were done, and 5 different treatments over 6 nights each. So here are the treatments. As a positive control, we have the open eaves and an open window. In all the 5 different cases, we have the door closed. The other treatment is with the windows screened and the eaves are open. The eaves are open and the windows completely closed, or the eaves and the windows are screened, and the last one, the eaves are closed and the windows are screened. And of course, without healthy mosquitoes, we cannot do this. So we had Florence rearing the Anopheles mosquitoes over here. She did a great job there, and research technician Miracle was trained to operate the cameras and the software to do that here with Remco from Wageningen University. And when we were visiting, and this was all done in Malawi, African parks, we were hosted, and there was wildlife around. So we also had some baboons, and we needed to protect our greenhouse, otherwise the baboons will climb on top and would destroy our equipment. So luckily African parks helped us out here. They had great experience in fixing these fences. So we have the cameras here in front of the experimental house, and infrared light is over here beaming upwards. And the infrared light will reflect on the mosquito wing, and the reflection of that will, at night, will be caught up by this infrared sensitive cameras. So we have 4 cameras, they work in pairs, and with that we could film the whole area of this side of the house, and later on make the 3D constructions with each of the pairs. So inside the experimental house, we had 2 sleepers, like I said, and they were protected with a bed net, and next to each bed there was a C2C trap to see how many mosquitoes were actually getting in. And we also used a Procopack to vacuum the mosquitoes from this house the next morning. And this is the front side of the house. We could move the eave panels, so we could move these panels with full closure or screen, and the same was done for the windows, and also the same was done at the back side of the house. Yeah. So that was exciting, and of course the first nights we really wanted to see how well we could track the mosquitoes online. How would the infrared light reflect on the wall? But this was absolutely no problem, and we could clearly see the mosquitoes from a distance. So we were confident that this would also work with multiple mosquitoes at the time. And we were ready to leave Malawi and leave Miracle and Florence to finish the experiments, but oh no, this was in March, and then the lockdown started, basically all over the world. But Miracle, what's in the name, he managed to continue the experiment with strict regulations with the volunteers, and all in all, we managed to finish all the experiments on time. Well, a small delay, but still, we're happy that we could at least do this. So we have some results. We haven't got all the detailed 3D results, but we do have results. And at first, I'd like to show what the different treatments did to mosquito entry. And it is in line with what we know from other house improvement studies. So the first 3 treatments where the eaves are open and the windows are closed or screens resulted in 30 to 50% of the mosquitoes that were eventually caught indoors by either the C2C trap or the Procopack vacuum. As soon as we close the eaves or screen the eave, we hardly find any mosquito back inside the house. So with this picture in mind, we of course want to know what's going to do this with the activity. And this is the activity for 1 hour recorded in the early evening. And we plotted the 2D activity, the 2D tracks over this picture of the house here. So this is, I only have 15 minutes, so I can only show you half an hour of time. But you see quite a bit of activity at eave level, mosquitoes flying close and also will fly in. And there is a mosquito flying in. So if you would do this for 1 hour, you get a result like this. These are the 2D tracks when we have different colors. We have 2 mosquitoes flying at the same time. If we do this for a full night, and this is the 16th of March with the eaves screens and the windows screens, we get spaghetti. We get spaghetti of data, and it's a lot of data to analyze. And of course, we need the tree data for this to see the actual flight parameters. So mind you, the blue lines here is not a single mosquito, but it's over a full night. It's each time one mosquito was in view and it made a track. When we have another color like yellow or orange, that means that there are multiple mosquitoes active at the same time. So clearly here with the eaves screens, there is a lot of activity close to the eaves. So the other thing we could do already with the 2D data is see whether this activity in front of the eaves, in front of the house, would also persist over the night and when we have a peak in activity. So we have the activity, the number of detected 2D points on the y-axis, and we measure this over the time 8 p.m. sorry, till 4. And again, all the treatments where the mosquitoes could freely pass the eaves do show activity, especially in the first couple of hours. But after that, it's not as much activity compared to the treatments where the eaves is closed or the eaves is screened. And we have really a lot of activity when the eaves are screened, the windows are screened in front of the eaves. And what's remarkable also, or nice to see, is that the activity is persistent over time, with peaking in the first couple of hours. So what do we know already? Well, first of all, we are happy and relieved that the online tracking works and we could film multiple mosquitoes in the same time. So we have a lot of data to process now. The mosquito activity filmed was successful for the 5 different treatments, the 5 different house conditions. And also, if you look at the capture data, it matches the data that we have from the field collections, not only in malaria, but other studies where there has been eave screening. We see this reduction of mosquitoes found indoors. So it's good to see that this can be matched later on with the behavioral data. And when the eaves are closed, the tracking data suggests that there's a high activity near the house. So the next step, obviously, we need the 3D paths, and we can do this shortly by combining the data that now we have. We actually find the flight parameters and really look at what's going on per individual mosquito that was in view of the house. So with this data, we can make the implications. What will this do when we modify the house? And I hope that we can link this to the modeling work of Jakob and Daniel, because it would obviously be interesting also to link this with the CO2 levels coming from the eave or from the window. And how can we target all these mosquitoes that stay here outside the house, in front of the house? How can we trap them? Where to put our trap with these mosquitoes to remove them from the system? And also, this will give nice information on other eave vector control methods like the eave tubes, for example. So I think it's really nice data to work with. Okay, thank you very much also for the funders, and I hope at some point that we see this great network together. I'm ready for questions. Thank you.
Thank you, Jeroen. That was absolutely fascinating. I love those pictures, the spaghetti pictures. Wonderful stuff with you and your team, Miracle and Florence. The questions will come at the end of this theme, and so we'll move on now to Majo, talking about the up and down houses in the Gambia.
Okay, thank you, Fiona. Good afternoon, everyone. I am going to present a project that we named the up and down houses. And what we try to do is to see if raising the houses has some effect in indoor mosquito density. We work with a lot of people and a lot of institutions, as you can see in this slide. So I'm sure most of you are aware of these facts, but I think it's important to mention them again. So most of malaria cases and malaria-related deaths, more than 90% of each occur in the African region. And now we know that 80% of the transmissions occur indoors and at night. That means that most of the transmissions are occurring inside the houses, and that's why it's so important to be able to protect people resting inside. One way of protecting them is with the millions of bed nets delivered in the region, and that has had a great effect, but we know that is not enough, and we can always do something else. So we conducted this experiment in rural Gambia, and we had this kind of an introduction to how housing in the Gambia is. So we have traditional houses that are built with mud brick walls and thatch roofs. And then there was a shift to a modern house that changed the roof with, to corrugate metal roof. And that also meant that the layout of the house changed from round to rectangular. And then in the urban areas, we have houses built with reinforced concrete structure or metallic structure that allows to have multi-story houses. In the villages we were working, we had traditional and the first modern typologies. So the up and down houses is an outcome of traditional knowledge and academic approaches. The first picture at the bottom, you can see a man resting on an elevated platform. And when Steve asked him why he was resting there, he said that because he got less mosquitoes there and he could rest peacefully. Then the second picture is from the Magoda project that you already saw. And they also have these elevated floors or second story houses. And the third picture is of our up and down houses. As you can see, they are aligned in their 4 different heights that go from ground level to 3 meters high. So I want to explain a little bit of the methodology of the study. We had 4 days each week, and we had 2 men sleeping in each house. We arranged the volunteers in pairs, and each pair changed house every day. So at the end of the week, all the sleepers had slept in all of the houses. We use CDC light traps for collecting mosquitoes. We have 1 light trap per house. And we also had 1 temperature and humidity logger and 1 CO2 logger. And for monitoring environmental data outside, we had a med station. Our houses had 2 doors, 1 at the front and 1 at the bottom. And each door had 2 gaps of 2 centimeters each to simulate the doors in the villages. And at the end of each week, of each experimental week, we move the houses up and down, which gave the project its name. So this followed the experiment design. You can see the houses are supported in a metal platform that was inside a metal frame. And this metal frame had 4 hoists that allowed us to move the houses up or down. These are the results of our experiment. This chart shows the mean number of female Anopheles gambiae in each house. You can see a clear reduction from the house at 0 meters to the house at 3 meters. And when we analyze for covariates like a sleeper pair, house position, or house height, and using the house at ground level as control, we saw that raising the house 1 meter meant that we had 41% less female Anopheles gambiae. And this percentage increased by around 20% with each meter. We also did some PCR analysis for a sample of the female Anopheles gambiae we collected, and most of them were Anopheles arabiensis or Anopheles colutzai, and almost none of them were Anopheles gambiae sensu strictum. I think it's important to say that even if there were a little percentage of Anopheles gambiae, there were none in the house at 3 meters. These are other entomological results for other vectors. You can see that for Manzoni species, there was also a reduction in the number of mosquitoes. But for Culex species, there was no reduction. And we think this is because they are used to feed on birds, so they will fly up into the, from the ground. When we included other Anopheles, some Aedes mosquitoes and other Culex, we found that there was a reduction in general for mosquitoes with increase of height. Here you can see the 4 charts and what I told you, 76.5% of reduction in Manzonia and 79% reduction in all mosquitoes. As I mentioned, we also measured temperature. Our houses were around 3 degrees Celsius warmer than the exterior temperature. And there was no such a big difference between the houses. We think maybe this is because the house at ground level, even though it was at 0 meters, it was not in close contact with the ground. So there was no heat transmission from the soil. Anyway, the house at 3 meters was the coolest from all the 4. When we look at carbon dioxide measurements, we saw that the house at the ground floor was the one presenting the highest levels, which is really problematic because CO2 is the one attracting mosquitoes to humans. And if mosquitoes fly maximum 1 meter above the ground, it will be really easy for them to find a person in a house at ground level. In this chart, you can also see how the carbon dioxide rises when the sleepers get into the house. And there is a decline as they go to sleep. But at 5, it starts rising again. And we think this is a reaction to the circadian rhythm when the body starts warming up in preparation for the day that is coming. At the end of the study, we had a focus group with the sleepers that you can see in the picture. Most of them said that they preferred the house at ground level or the house at 3 meters. And they said that they didn't feel a major difference in temperature or mosquito numbers in the houses at 1 and 2 meters. They also said that they would be happy to have a house at 3 meters if the house would be built with their traditional materials. So not using the traditional materials is not only a limitation for the implementation of this project, but also for the experiment itself, because as you heard before, different materials have different effects in indoor temperature and indoor comfort levels. Another limitation was that our houses are smaller than an average house in the Gambia, and that because of the design, our houses worked as single isolated houses, which is not the case in the context where houses are line houses. That means that one room is next to the other. We also changed the volunteers' sleeping time. For our experiment, they had to be inside the houses at 9 at night, and they stayed there until 7 the next morning. In reality, people will stay outside their houses up to midnight or 2 in the morning, and then they will leave their houses around 6 for the first prayer. So that was different. We also think that if we raise houses, people would like to use the ground space. and that means that they might have walls, which might guide mosquitoes up to the people resting. If we raise the houses, mosquitoes might change their behavior, also locating the hosts. This slide is important to us because we had some comments that raised houses do not belong in sub-Saharan Africa and that they are from Southeast Asia or Latin America. And that is not true. So we have some examples here. The first row are some agricultural raised houses. So these are for storing crops, and they are raised to avoid, for example, rodents. The second row are some houses on stilts into lakes, and these are mostly informal settlements in Benin and in Nigeria. And the third row are houses, two-story houses that have one use in the ground floor and another use in the second story. The last picture is from the Gambia, not exactly from the same location we conducted at our experiment, but still the same country. So before I finish, some take-home message. The number of malaria mosquitoes entering the house reduces with increasing the height of the houses. It is less likely that a mosquito finds a person resting on an elevated house. And raising a house 3 meters is equivalent to the protection that a bed net provides. And we do recommend raising up the houses because it won't only protect people, but it will make houses less warm and more comfortable, which means that people will be more willing to use their bed nets. Thank you.
Thank you so much, Majo. That was great, and how satisfying to get such a clear-cut result, and it tied in so well with the CO2 levels. Fantastic. So now we move to the panel discussion, and I think I might share my slide again just to remind people. People are recording, posting their questions in the chat, which is exactly right, and I see that speakers have been answering those questions as we go along, which is also good. There is a possibility also to raise your hand, but I think working in the chat is probably for the best. Just
Fiona, I noticed that in the chat, panelists are asking questions to each other, and I think it's nice that also all the attendees can see these questions. So maybe we should watch that.
Yes, good. Yes, people. So when you put things in the chat, just down at the bottom, you can you flag up who you're addressing your questions to, and choose panelists and attendees, and then everybody can see what's going back and forth. That would be really useful. Now I've lost my chat again myself. Perhaps I better stop screen sharing. Heather or Alex, how do I see the chat if I'm screen sharing? Do I have to come out of that?
Yeah, no, I've just emailed you all of the questions if you're able to go to your email.
Oof. Well, that could be. Hold on.
I'll send it in the chat to you.
And to see the chat, Fiona, I think if you click on if you hover at the bottom of your screen, it should come up with a toolbar, and you can click chat. Sometimes
it's not doing that while I share my screen, so maybe I should come out of sharing my screen.
Okay.
But in the meantime, I can see there were a couple of questions. If you go up to the top, Steve, in the Q&A, there were a couple of questions that we could start with. Yeah. You want to go to here, Steve?
Should I start with the primer question about the
Yes, that's the one I was looking for.
comfort
Yeah.
zone? Yeah. So
Yeah.
the primer is asking, is the comfort zone unique for all age category? It seems like it's quite unique. It's quite universal that the people tend to like the same temperature, and despite age, height, or ethnicity, or wherever you go in the world, people would prefer more or less the same climate. We know this from big studies done in the 60s and 70s, where you would fly in people from all over the world, put them in a climate chamber, and ask them to adjust humidity and temperature until they felt comfortable. And people seem to prefer the same temperature. You would think it would be different if you were born in a very hot climate, but it is quite similar. There's still a natural distribution, but people tend to like the same. The only thing, but there's some modifications, but overall, people do like the same climate all over the world, or prefer the same climate. And then it's to Majo, I think, the next one. Yeah.
Yes, let me think. Let's find the one. There is one to Majo, also from a Brimer, and he's asking why the CO2 is high in the hut, which is at 0 meters, when the indoor temperature is almost the same.
We're not sure about that, but the difference in temperature that might not seem much for us in the chart, our bodies can really feel them, and we think that if the temperature increases, we produce more CO2. Yeah, that might be. And there was another question from Lucy. Yeah, they said that they prefer the traditional materials because they felt more protected. So the hats were from marine plywood that is really thin, let's say, and they are just used to their traditional materials.
Thank you. This is one from Steve to Jakob Daniel, asking about whether the shape of the bed net would influence carbon dioxide movement in the house, because many of the nets are rectangular rather than cone-shaped.
To some extent, it would probably. I'm answering also. Daniel, I think, has left now. He had to do another lecture at the same time. Yeah, but it will affect it somehow. But I don't think it will affect so much what's coming out of the house in terms of you could say the end result, whether it goes to the doors or to the eaves or whatever. There's another question which is also, but I mean, it's easy to model different nets. I think one of the big findings of this study, the last one I see from the Magoda study, is that nets it's not only a net, it's kind of a distributing surface. So if you have a net around something, it kind of levels out the CO2 on all the surfaces. So it means that there's no buildup of CO2 anywhere. That's why it seems to be quite good for these houses. The more big netted surfaces you can put on, and it also, I think, this explains some of the other findings. For instance, in Jeroen's, that even small holes might still attract mosquitoes, even though you have closed the eaves. There will still be some activities because the small holes will have a high CO2 concentration via small hole, and therefore a big difference in concentration. So I think we are kind of getting to the understanding that it's all about not an absolute concentration, but differences in concentration.
So, may I say something on the subject of carbon dioxide production by people? I think one of the importance to consider is that there's not a linear relationship between CO2 reduction and temperature. And I think that if you start getting temperatures of 30 degrees centigrade, the body starts putting a lot of energy and effort into trying to cool down. And I think that results in increased carbon dioxide, sweating, bodies trying to keep cool. So Lindsay's rule of thumb, anything over 30 degrees, bad news.
Yeah. I agree.
We have a question from Manuel Luberas to all panelists, saying that we've mentioned nets several times in all the presentations, but is there any effect on the impact of indoor residual spraying? I guess in relation to carbon dioxide, I assume in relation to carbon dioxide movements and mosquito attraction.
Well, for carbon dioxide, I wouldn't see the link, but for the spraying, it's of course interesting to see whether it has a repellent effect, and this we could measure, but I have never done that. We did do it for insecticide impregnated nets, and then also filming the mosquito behavior outside the house again, and there was hardly any effect, so there was no spatial repellent effect measured from the nets. Closer to the net, that's work done by the Liverpool School by Philip McCall. I also answered this in the chat. So I'm not sure whether that answers the question. But of course, this could be answered with the same setup that we used here.
Mm-hmm.
So Lucy was also asking whether you could model other odors, and I think that's kind of the same line that you know, how would different chemical compounds influence each other? And you can say in CFD as a tool, you can model any gas, any liquid, anything you can describe physically. You can model, and you can model them side by side and say, if you have a temperature and you have this molecule, how would it kind of distribute itself, and how would CO2 do? And you could take any gas, anything, and for that reason, you could of course also model how spatial repellents might kind of get around in space if you know the physical properties of the compounds.
Thank you. And Vincent Luo has asked again to all the panelists: is there any difference for the building in rural versus city for attracting mosquitoes and malaria infection? I guess the short answer is maybe we don't know.
I mean, the building physics are the same in rural and urban areas. The physics of the building will perform in the same way, but there might be more mosquitoes in rural areas, or different types of mosquitoes depending on the environment. But the building physics are the same. You can say in many ways, it's different types of problem you will have to solve if it's, say, a multi-story house in an urban setting. It would perform much different from a single-story house in a rural setting. But the overall geometry and the building components are the same.
Thank you. And a question for Majo as to whether or not with the acceptability of the raised houses to families and with small children, whether you had any insight into that.
Yeah, I want to make a little comment on the previous question. Okay. I think that because cities are more dense, that might change how wind moves around, and like the wind that goes into the house, and that might change mosquitoes getting into a house or not. That could be something. And we asked informally, we didn't have a proper focus group with women, but when we were building the houses, the people that asked more about the houses were women and children, not men. That was curious for me. And yeah, they said that they like the houses at 3 meters, but we never got the chance to take them into the houses.
And we have asked in Tanzania. We did first 4 houses up in Magoda, and now we are building all these 110 houses in the south. And people are really happy to have 2-story houses. They think about it as something really attractive. We have not met anybody yet who would not prefer a double-story house or a single-story house. People really like to have a double-story house.
And it is your impression that they would like to, they most likely would fill in the space underneath houses? Well, in fact, they are filled in, aren't they, in your Magodi study, I believe?
Yeah, it's a bit mixed. Some of them are filled in and some are not. So we've tried both. And yeah, I think we don't know whether they prefer one to the other in that sense.
Okay. And we have another one about the house height here. Emmanuel Temu was asking, does the weather affect the indoor CO2 levels? Did you notice any effect of weather variation on indoor CO2 levels? And lots of questions. How would you explain the lack of differences in the density of Culex mansonia relative to the house elevation? I guess we'll start with the weather and the CO2 levels.
Yeah, no, we didn't notice we didn't, like, I have to check on the data, but I don't think there was any relationship between CO2 and weather. I have to check though. And that's an important point, thank you. And for Mansonia, there was a difference, reduction when we raised the houses. For Culex, there was not. And we think that's because they are bird feeders, so they will fly up anyway to find blood.
Thank you.
Maybe you could say that if it's windy, then the CO2 is washed away. Then there's better ventilation, and so there will probably be a stronger effect if it's an evening where there's hardly any wind and it's very hot and humid. There will be more mosquitoes finding the house. And I think that's also what you kind of feel naturally, that might be the case. But if it's very windy, they can't, the CO2 is washed away.
Thank you. Well, questions are coming in thick and fast. I'm hoping, as I say, we will be collating all these later. So apologies if I've missed yours, but there's one here, a question for Jeroen, and saying, between eaves and windows, considering both closed and screens, what would be more effective in preventing mosquitoes from entering the house? And what would you suggest to national malaria control programs? Big question. What would you suggest to them, taking into account the socio-economic status of populations in local areas?
Yeah, I saw this question coming from Jesse. I saw a couple of other questions. So this is a great question, and I'm not the one responsible to answer this. And it's also too early based on our data, but what we see in general is that eave screening is really effective. So I would go for screening the eaves, and even also in other countries, and this relates to the question that Ann Wilson had, why would a mosquito stick for so long to the eaves even when they are closed? And this is seen often, that the mosquitoes hang around in this area close to the roof. In any case, even in countries where they don't have eaves and where they wanted to make the eave tubes, there were no eaves, but still they found the mosquito activity immediately as soon as the eave tubes were there. So this is also natural behavior of the mosquito. So I would go for eave screening if you have no choice. The nice thing that the project in Malawi, they did have a huge program around the national park where people themselves did the eave screening. So with minimal financial support, the local communities managed to close the eaves themselves just by getting a bit of screening. So it's also really cheap. So I think that would be a great recommendation for many, many countries. If I can continue, Fiona, I gathered on a couple of other questions from the chat, if I have time.
Yes, let's do your couple of questions, Jeroen, and then I think we'll stop for our break, but go for it, yes. Yeah,
okay, Nakul Chitnis asked how many mosquitoes you could track at a time. Well, right now we are like 25% of the maximum capacity, and we could do at least 10 mosquitoes at the same time. At the very last day before we left back, we decided to work on a single laptop with 4 cameras instead of 2 laptops on 4 cameras. With the 2 laptops, we could do even more, so we could do 25 or 30 mosquitoes at a time. But this was safer, so we left it on 1 laptop. We were using FlyDraw software by Andrew Straw. And Musa Jarawa, why I deliberately left out the temperature data? No, I did not, but I did not have time. And we had 3 data loggers, 1 inside the experimental house and 2 in the screen house. We did not look into detail yet on this data, but of course we will do that to see of an effect. But ideally, I would love to have all the hobo CO2 loggers and do the CO2 measurements also with the modifications, but we simply couldn't do all these things within this small project. So it would absolutely be great to link this project with Jakob and Daniel to this flight behavior data. So thank you.
Thank you, everybody. I think we should stop for our break now. And I believe that the Global Health Network team are going to put a timer on and set with a countdown. And if we could come back at 20 to 2 to continue, but really interesting projects and good discussions, so fantastic. And we will answer questions. I suggest that we'll put them on the BOVA network website, and I'll just check with the Global Health people, maybe we can put it on theirs as well. But see you all back at 20 to 2. Thank you.